Good morning, everyone, for our weekly Slightly Brighter and Earlier lecture. I'm glad to see so many of you made it out of bed this morning. But someone special also had to drag himself out of bed today. Junji is back from his Taylor Swift concert, having won the tickets from last time, but he's got a few questions for the class. He wasn't sure quite all the details of the music and so wants to ask for your advice. He wants to know, what notes did Taylor Swift play? You see, he's a really big fan, and he's an amateur guitarist as well, so wants to know how can he play the same Taylor Swift songs. So our motivating question for today is, if we take a recording of the Taylor Swift songs, how can we get back the notes that she played in order for us to notate down the music and so that we can play it on our own? So our first question is so we've got a sound recorder. How are we actually going to store the music? How are we going to represent this on our file system? How are we going to manipulate it in C and then eventually convert it into musical notes? Well, one thing that we can think about is what actually is music? Well, it's these vibrating air molecules, and they're all moving at different speeds, and those different speeds equate to different frequencies, and then when they hit our eardrum, the vibrating air molecules are moving at slightly different speeds, which makes our eardrum vibrate, and then that gets converted to electrical signals. There's some kind of encoding going on there that then gets sent to the brain, and we experience the joy of Romeo and Juliet as sung by Taylor Swift. So what we're going to try and do, one way of representing this might be to measure how fast the molecules are moving. Perhaps we can have a microphone that measures the molecules as they hit it. And then we're going to capture how much the thing was moving at given time intervals with a distance of delta t. So let's say the thing was moving very fast at time t1, a little slower, it was a little less displaced at time t equals 2, a little less displaced at times t equals 3, because there's a correlation between the displacement as well and how fast the things were when they were moving and how much energy was taken in. If you want to learn more about that, we can go to a physics class, but for now we're more concerned about the representation in computer science. So let's measure how fast, that seems a little tricky. Instead, let's measure the amplitude of the wave at intervals time t. And we can figure that out based on the movement of our microphone. Okay, so we've got a basic strategy for our recording. We are going to take a bunch of different samples at certain intervals and use this to represent the waves. And then when we want to play it back, all we have to do is get our speaker to vibrate the same way as our samples. And if our samples are close enough together, so let's say we capture samples 44,000 times per second, which is standard for a normal musical recording, then when we play it back, hopefully our ears won't be able to tell whether it's being performed live or whether it's coming out of just a really nice speaker, because our speaker should be capturing all the important characteristics of these motions of molecules. So again, kind of lofty, we're still not at the point where we're ready to put it into a C program. So this is what a representation of Taylor Swift's first note looks like. Now, if you were to actually listen to this, I can promise you it would be a pretty boring song. In fact, it might hurt your ears a little, but we can see here that I put a bunch of samples at evenly spaced intervals, and depending on where I placed it, I can measure the amplitude of the wave at that point. So at time between time 0 and time 0.002, you can see there's a peak where it hits amplitude 1, and then at some point later it goes down, it comes up again, and we get this nice repeating pattern. So this is our one-note Taylor Swift song. Seems easy enough to represent. Does anyone recognize this kind of pattern? What does this look like? All of you have taken some maths. Yeah, it's a sine wave. So if Taylor Swift is playing a perfect sine wave, we're going to hear this note. But hopefully Taylor Swift is playing something a little more like this. Now, this is still not going to sound great, but at least it'll have a little more vibrance to it. Do we have any musicians in the audience? Anyone? No one plays an instrument in here. Yeah, remind me your name. It's been a while. Perrin. Okay. Perrin, what do you play? Piano? Do you know what this is? Could be a scale, but it seems to be repeating over and over and over and over. So it's likely to be just one combination of notes. But we'll get back to it a little later. Still, we have a mysterious figure on the board. We're capturing our samples. And we want to figure out what this actually is. Maybe it's something on the piano. Maybe it's something on the guitar. Maybe it's something generated by a signal generator. We'll find out. But one interesting characteristic that's going to be important when we try to represent this is we have clustering of samples at the very, very top, like at the very, very high amplitudes. And then we also have clustering of samples right around 0. Our middle line here is 0. And we have a whole lot of values that are very tightly spaced together. So if we want to represent these numbers, what C-type should we use? Perrin's lucked out this morning being our piano player, so he's going to answer a few questions for us. Do you want to pass that back to Perrin? Okay, Perrin, what C-type should I use to represent these amplitudes? So they're between -1 and 1. And you said we should use a float. Now, what's the problem with floats that we've talked about a little in class already? What are the two types of floats we have? Yeah, it is going back to week 2, but when I gave some advice to everyone, and that was never use the float type. Why did I give that advice?
I do remember hearing this.
So, do you remember something about how accurate float types were, perhaps?
Yeah, I think it's some point they start screwing up.
They start screwing up. They contain only a limited capacity to contain significant figures. Now, we've got some really big numbers here, or numbers very close to 1 and some numbers very close to 0. And so if we look at how many figures we're going to need for the very small ones and how many for the big ones, it's going to vary. So even using an integer might run us into some trouble as well, because we're worried about the number of digits. So it would be maybe tricky to just scale an integer. Let's return to this problem in a second. Perrin, you can turn that on mute for the minute. But our figure here looks like a mix of different sine waves. So maybe by the end of the lecture, our goal is to figure out a way to extract the different sine waves that we've combined here. And once we can extract the different sine waves, we can measure their frequencies. And when we measure their frequencies, we'll know what combination of notes are being played. And as we said, there are very different amplitudes going on here, which means we need to worry about accuracy both at the large scale, close to 1, and at the small scale, very close to 0, so when our numbers have lots and lots of decimal places, which is going to lead to some questions about how we're going to represent them and what C-types we should use. So for your well-being, I've put together a list of requirements that we're going to need for our number representations. And indeed, as much as I would love to talk to you about Taylor Swift and musical instruments and piano for the rest of the lecture, unfortunately, we're going to spend the bulk of our time figuring out actually how to represent these numbers in C, because this seems to be the largest stumbling block from us in actually representing the music and manipulating it. So here's the list of things that we need for our numbers. We want our numerical operations to be correct, so we want when we do a basic mathematical addition, we need some notion of correctness, otherwise why are we bothering? We want them to be efficient, so when we actually make a computer that manipulates these numbers, it has to be fast enough that we can do 44,000, capture 44,000 samples per second and manipulate those samples and store them. We want it to be easy to implement so that you guys can actually graduate. Effective so that they're useful for the task at hand, and in our case, we've got some numbers close to 1 and some numbers close to 0, so we need to be effective for this task. And then we've got some other maybe question marks here. So we'd like it to be predictable so that we know even if we're losing some accuracy, because remember, when whatever number representation we have, we do have to sacrifice some accuracy. Computers are not perfect and they have limited memory. Able to represent very big and very small, and also able to scale to arbitrary precision. So maybe if I say that, 13 decimal places aren't enough, I actually need 17 significant figures to be correct. Maybe we'd like to have a way to get our numbers to be able to represent more and more significant figures as we need, or at least scale a little bit as the size of our numbers changes. So these are a bunch of possible things that we would want for our floating point numbers, for our fractional numbers. If we're talking about integers, perhaps our list would look a little bit different, but this seems to work for us for the minute. So Perrin, I'm going to pick on you again. Given all of these, so let's go back to basics. Instead of thinking about C-types, if I want to represent one of these numbers that we're using for the music, what is one way of storing a number with a decimal point in it? Just come up with it on your own. What do you think? What's the simplest way to do it? Okay, I've given you a bunch of bits in your computer's memory, and you can flip them either on or off. How are you going to represent, say, the number 0.5? Or let's make it easier, 0.1.
Suppose you just have a byte that's a 0 and a byte that's a 1. So it's a decimal point.
Hold it a little high so everyone can hear.
Suppose you have a byte that's a 0 and a byte that's a 1, and just...
So we're using bits, right? So you said have a bit that's a 0 and a bit that's a 1. And so we could, what is the 1 bit and what's the 0 bit? Just remind me. I said the number was 0.1, so...
So there's 0 and 0.1 and 1.
So you're saying have a ones place and a point ones place in the number?
Yeah.
And then if I wanted to do 0.01, how would I represent that?
0, 0, 1.
Okay, so you're saying let's maybe make space for 32 numbers after the decimal place. So I then have a ones place, a tenths place, a hundredths place, a thousandth place, a 10,000th place. And then all I do is remember that this number is going to be scaled. So I write a normal integer, and then I remember that whatever the integer is, I have to scale it a certain amount. So what are the different ways I could do the scaling? So let's say I now want to represent the number 3 in normal binary. Do you remember how to represent the number 3? So we start at 0. Then what's next? Let's just count up together. What's after 0? Well, counting in binary. 0. How do we go from 0 to the next number? What's the next number after 0?
1.
Okay, so I have a 1.
Yes.
Now, I've used up my ones place.
Yes.
So if I add another 1 to my ones place, but, well, that's the wrong finger. Let's hold it up for the minute anyway. But I have a 0 in the ones place and a 1 in the twos place. And now if I want to get to 3, add another 1. So there's my 3. Yes. Now, if I want to do 3.1, what do I do?
Suppose you need something to signify a decimal point.
Yeah, so I could say, let's save the last place for our tenths column, or let's save the last 2 places for our tenths and our hundredths column. So what we're going to do is we'll just write our number as an ordinary integer, and then we'll save off some of the places to be our places for all the numbers that come after the decimal point. So that's one way of doing it. Just break up your integer, and use normal integers in C, and then just multiply them by a fixed amount. So given that we can save off, say, 4 of the places, then we get 2 to the 4, a maximum of a number of 2 to the 4 after the decimal point, and then we'd use the rest of the bits for the number before the decimal point. So that's our basic version. Perrin, I think you've probably had enough for the minute, so let's pass off the microphone, maybe to Belle. Belle, do you feel like it? Okay. So what is the problem with this representation?
What's the problem?
Yeah. So what numbers can I represent in this representation? Where I've said I have 2 to the 4, I can store up to 2 to the 4 after the decimal place, and I can store 2 to the 28 before the decimal place.
Well, then that's your limit, right? You can't store anything bigger than that.
Yeah, and so what's another strategy that you might think?
For storing something bigger?
Yeah, well, let's say that we want to be able to be more flexible about where our decimal place is, because maybe there are more numbers after the decimal place than before, or maybe there are more numbers before the decimal place than after.
Can you use a bit like you do for sign? Can you use a bit to say where the decimal is?
So how much information would 1 bit give us about where to put the decimal place?
It can only be a 0 or 1.
Yeah, so that would only tell us either it's in this position or not in that position. So what if we use some more bits? What do you recommend?
You're going to use too many bits, aren't you? You can't just keep adding bits and bits and bits to say where your decimal.
Well, that's true. 1 integer is 32 bits, but we're not limited to 1 integer, are we? So what would you do? If you say, I want to choose where the decimal place is and I want to represent it some way, and I say have as many integers as you like, what are you going to do?
You use an extra whole integer?
Yeah, we could use an extra whole integer to figure out where we're going to put the decimal place in that number, and then we can still have the same number of significant figures in our number, but we'll just use another integer to represent where that decimal place is going to be. So that doesn't sound bad.
But how do you connect the two? How do you keep them?
So remember, we're excellent programmers. We can make a struct. And inside our struct, we can have this definition, or we can build it into our programming language. We can tell our compiler how this works. And this is actually called fixed point arithmetic, and unfortunately is not a feature of the C programming language. So despite the fact that this is used mostly for music processing and for machine learning, it's very, very common. C doesn't have it built in. So if you want to do this, you're going to have to implement it yourself. But instead of having two integers, on a modern computer, I have 64 bits in a standard integer. So what's my other option? Microphone bell.
You can split it in half, right? If you only need 32 bits, and 32 bits the other one. Can you use half each?
So yeah, I could say let's split up my one integer and store where the decimal point is in part of that integer. And so I'll have part of the integer will be the sign, whether it's positive or negative. Part of that integer will be the significant bits. And then part of that integer will be where the decimal point is. So really, we're no longer talking about integers. We're just talking about a group of bits that is the word length of our computer. Because remember, we have the natural unit for our computer is called the word length. And if that's 64 bits, then we can break up that 64 bits into some to tell us where the decimal point should be, some to tell us where the number should be, what the significant bits are, and some to tell us of the sign. Now, we're already used to a form of writing that tells us how many decimal places should be in the number when we write it out in long. What if I give you the number of atoms in the universe? I'll tell you it's a really, really big number with a lot and a lot of zeros. I'll tell you it has 82 zeros. How would you write that down? You're in a physics class. How are you going to write down that number for me? Keep speaking into the microphone, otherwise people online won't hear you. Have you ever done physics?
No.
Okay. Who here has taken a physics class? Okay, maybe pass the microphone all the way to Miguel. Okay, Miguel, I have a really big number. How am I going to write it down?
We use times 10 to the power of.
Yeah, we times 10 to the power of. So for example, just give me a big number.
8.2 times 10 to the power of 100.
So this is doing the same thing, right? We're telling ourselves where to put the decimal place. And instead of saying which position to put the decimal place, we're saying assume that we're talking in scientific notation. So this is always going to be a power of 10. And then all you need to know is the exponent. So for example, if it's the number of atoms in the universe, the exponent might be the number 80. And so if you store the number 80 alongside your significant digits, then you can figure out what the number actually is, and you don't need to write 80 zeros after it. What about really small numbers? How do we do those?
Same with -10.
With a negative exponent. Okay, so this gives us a bit of a strategy for how we're going to represent our numbers in floats. Yes, Afan. Do you want to pass the mic to Afan? Thanks, Miguel.
Yeah. Just a question. So that's for near zero values. So then what about near one values? Because all of them have a value inside.
So the strategy still works. You choose how many significant figures you want, and then if they're near 1, you multiply them by, for example, 10 to the negative 1. No worries. But keep the microphone on though, because now I've got a question for you now that you've picked up the microphone. So I'm choosing what what my power should be. So for example, I could do it 3 by 16 to the 4, or I could do it 3 by 12 to the 7, or I could write 5 by 6 to the 52. What number should I be multiplying things by, given that I'm on a computer?
Would it be 2?
Yeah, powers of 2 make sense. Why? Because this is the way that computers are architected. They're architected around bits, and so they're very, very efficient when we use powers of 2. So this gives us our strategy for representing numbers that allows us to scale where the significant figures are going to be. We're going to store the sign in 1 bit. We're going to store the significant figures in what we will call the mantissa. That's just a fancy word for significant figures. And then to calculate the number, we take the sign, the mantissa, and then we multiply that by the base, which Afan said, what number are we always going to use for our base in computing? 2. And then multiply that, raise the base to the power of the exponent, which we're going to store in some of the bits. So as an example, we have negative 5.432, that's the sign in the mantissa, multiplied by 2 to the power of 3, where 3 is our exponent and 2 is our base. And we're going to call 2 to the power of 3 the characteristic of the number. But we don't actually need to store either the 2 or the characteristic. Why not? We don't need to store the characteristic as a whole, I should say. So we don't store the 2. We don't store 2 to the power of 3. What do we just store? Yeah, we don't need to store the base. We can just store the 3. Because we're already on the computer, our computer's efficient at dealing with powers of 2. It's got a bunch of built-in operations to deal with it. So when we actually do our bit representation, we're going to drop the 2. So this gives us another question, though, which is how many bits should we use for each of the parts? Well, this depends on where you want your accuracy to be, like how many significant figures you want to have, versus how big and how small you want the numbers to range between. So the answer to this is just decided by committee, called a standards body, and in this case, it's the IEEE standards body. The standards body, this IEEE, got together, and they came up with a document called IEEE 754, that's just some arbitrary number, and in this, they said, this is roughly how many bits you should use for each of these parts, and we're all going to use this on our computers. And what were the numbers? For a float, they said, let's put approximately 24 bits in the mantissa, and for a double, let's put 53 bits in the mantissa. And so this gives you a perspective on why we should really be using floats most of the time, because for not very much added memory cost, we get a lot of extra precision in the number. Now, I did say approximately, and you think, well, if they're a standards body, surely they're being a little more accurate than this. That is true, but there are some details around exactly how they're stored that we're not going to get into that leads to this approximate value next to it. Is there any questions on this so far? Yeah?
Does the C committee not have anything to say in this?
Well, all the different standards committees are interrelated. Many of the people who sit on one standards committee are on the other. And at various different points in time, there are, the development of programming languages also follows the development of technical standards. So in this case, the IEEE community got to it before the C community, and so the C community adopted the IEEE standard. That doesn't mean that C didn't have floating point numbers before. I actually don't know the history of this standard, but very often a standards body will look to practice to see what the standard should be. So it might very well have been the case that C was already doing this, and then the IEEE were just the ones who formalized it. But to do that, we'll have to dig in a little more into the history of the standard, which is probably on Wikipedia. Okay, so we've gotten a little further along, but we still need to know how to actually write down our representation in binary. We've come a long way, we've still got some work to do. So these are the steps codified in the standard. Admittedly, I've taken some liberty and rewritten them out myself for your enjoyment for how we're actually going to do this. So here is our 32-bit number at the bottom. If it's 32 bits, what am I using, a float or a double? I'm using a float. If they're 32 bits, there's definitely not enough. There aren't 53 bits there to store the mantissa in. And I've highlighted for you the bits that we've got for the exponent, the bits for the sign, and the bits for the mantissa. And this is actually the correct order in which you're going to store them. So you store the sign, then you store the exponent, and then you store the mantissa. So the first thing to do is to write out all the significant figures in binary. Then what we're going to do is we're going to make it just like in scientific notation, so there is one digit before the decimal point. Then we're going to encode the significant figures in the green bit, store the sign, and then we do something a little weird. So instead of writing the exponent directly, because we're going to want positive and negative numbers, we're going to need some way to represent both positive and negative numbers, and IEEE is not using 2's complement. Instead, they just pick some arbitrary number. In this case, for floats, it's going to be 127, and that's called the bias. And every number above 127 is going to allow us to count the positive numbers, and the numbers below 127 are going to be the negative numbers. So 127 plus 1 is 1. 127 plus 2 is 2. 127 plus 3 is 3. And then we're just going to write those out in standard binary over there. So we also now have the task of converting fractional numbers to binary, because I've said just write it out, but I haven't actually said what the process for that is. So this is going to be our process. First, just write out if you have a fractional number that doesn't have a whole component. So if we're just computing the fractional, start off by writing 0 and then the decimal point. Then what you do is you multiply the fractional amount by 2. Now don't worry if this is abstract, we're going to do it concretely in a minute. So if the number is 0.5, multiply it by 2. Separate out the leading digit. So what's the first digit of 0.5 by 2? It's 1. 0.5 by 2 is 1. That means the leading digit is 1. Append the leading digit to the final representation. So that becomes 0.1. And then if there's anything left other than the leading digit, then just repeat the process. Multiply it by 2, take out the leading digit, and then take what's left, multiply it by 2, take out the leading digit, and so on and so forth. Now, do you want to pass the microphone forward to Angela? What problem could we run into with this process?
I don't know.
So when does this process stop?
When the number ends.
When the number ends. But when does a real number end?
Oh, it doesn't.
Yeah, a real number doesn't end. And even worse than that, we can get recurring numbers. We can get numbers that, when represented in base 2, have an infinite number of digits. So what do you think we should do about that?
Well, we should define when it's going to end.
Yeah, we should define when it's going to end. And what do you think? What do you think is reasonable?
I don't know. When you reach some sort of limit.
Yeah, let's go. What were you going to say? Yeah, we pick some limit, some number of significant figures that we're going to represent, and we stop once we're out of significant figures. So we are going to lose precision one way or another. There's no way around it. But we do set ourselves an arbitrary finishing point. Or, because some numbers just have a long trail of zeros, instead of writing out all the zeros to an infinite number of zeros, if we see that there's nothing left in the fractional part, we just stop there and leave everything else at 0. So now let's actually try this out. Thank you, you can put that on mute. You're off the hook for now. And we'll pass the microphone to a new location next. Let's actually try this process. And we'll try it with a couple of different examples. OK, let's do it on 0.625. And who wants to work through this example with me? Anyone? There's a definite no from Perrin. Jaslyn? Nah. OK. I forgot. Kevin? Keith. Close. OK, Keith's going to help us out here. So what was my first step? What do I do with the number? OK, what do I get? 1.25. What's the leading digit?
1.
Leading digit is 1. Oh, what have I forgotten? What do I have to start with?
0.
OK, 0 point.
Yeah, and then you take off the leading one.
Take off the leading one.
And then multiply it by 2 again.
Multiply that by 2, so I get 0.5. What's the leading digit?
0.
0. OK, so I'll write down my 0.
And then multiply it by 2 again.
Multiply it by 2.
And then take the leading digit.
Take the leading digit. And now what?
You're done.
I'm done? OK, so I just fill out the rest of my significant bits with zeros. Let's try another one. OK, let's do 0.175.
So 0 point. Start with 0 point and then
OK,
multiply by 2, which is something. 2, 3. 2.35?
3, 5. Right?
Yeah, and then take the leading digit,
What's the leading digit?
which is 0.
Yep.
Multiply by 2 again. Yes, sorry. First we're leaving digit out and then multiply by 2 again, which is 0.7. Take the leading digit within 0. Multiply by 2 again, 1.4. Take the 1. Multiply that by 2 again, 0.8. Take the 0. Multiply by 2 again, 1.6. Take the 1. Yeah, 1.2. And then take the 1 again. And then you get back to 0.4, which we've already for the disk. You get 7.
Okay. So at this point, we're going to have to stop ourselves, and we will just leave it there because we are going to get into this situation where we get to 0.4 again, and we've already seen our 0.4, so we're just going to start writing recurring digits over and over. So that would be, did I write that one for the 2? Yes, I did. So now we'd have another 0 again, and then we go back to 0, 1, 1, 0, 1, 1, 0, 1, 1, etc. in the loop because we've already done that. So there is our process for converting fractional numbers into binary representations. So now that we do that, we can also do it with mixed numbers that have both a decimal component and a binary component by just treating them separately, treating the component before as a regular integer and treating the component after by decimal, and then multiplying or scaling appropriately. So now we're ready to do a demo of the full IEEE 754 representation. And who's going to do this one? Junji, you appeared at the very start of the lecture, so I know you're very excited about this topic. So you're up for helping us through getting the full representation of 14.5 in IEEE 754. So Keith, do you want to pass it down? Thanks, Yulong. Okay. Our number is 14.5. The things we need are, this will be a little hard to see, I think. We need a sign. We need our mantissa. And we need our exponent. That'll be. So let's start off. What's the sign? It's positive. That's, the microphone's off at the moment.
Hello, hello.
Hello, hello. Okay, so what convention should we use for our sign? What did we use for integers? Was 0 positive or negative?
Positive.
Yeah, 0 was positive. Okay, so is this a positive or negative number? Positive number, so what do I write? 0. Okay, next up.
To express 14.
Yep, express 14. So what is 14 in binary?
14 binary.
So quick thing, is it bigger or less than 16?
Less than 16.
It's less than 16, so it's going to be 8. Will be the.
8 14. So 1110.
Yep, 1110 is our 14. And then we have a fractional part as well. That's our 0.5. We've already said what 0.5 is. 0.5 is just 0.1, so let's put our 0.1 in there. Yep. And now the next step was I have to normalize it. So I only want one significant figure before the decimal point. So what do I write here? If I'm going to express it as significant figures by 2 to the power of something. So only one of the numbers can be before the decimal point. So what's the first number in this binary representation? What's the first? It's a 1. It's over here. It's just a 1. So then I write my decimal point. 1, 1, 0, 1.
Yeah.
And now I have to multiply this by 2 to the exponent. So what's my exponent going to be? How many decimal places have I shifted it? 3. Okay. So now we have our number written out in the right form. Now we need to do the correct encoding for IEEE 754. So remember, the next few bits in here were a little weird because they had this bias term. We didn't just write 3 directly. Do you remember what the rule was? I said that there was like a number 127, and then the numbers above it were positive and the numbers above it were negative. So 127 plus 3, so it's 130. And now we write 130 in binary.
Okay. So it's larger than 128?
It's larger than 128, so let's put a 1 in the 128ths column.
Yep, and a 2, so one how many out between this? The 64 is O and 32 is O, the 16 is O, and 8 is O, 4 is O, 2 is 1.
2 is 1,
And 1 is O.
and 1 is 0. Okay, so that's 128 plus 2 is 130, and so that's our representation of the exponent. And now we've just got to write in the mantissa, and all we do for this is we write it indirectly. So because we know that our number at least has to be multiplied by 1 in this case, we're just going to write these bits in. So 1, 1, 0, 1, and then a lot of zeros. So now let's check it. And there. And there is our final representation, possibly a little hard to read, but can we have a round of applause for that tricky calculation that we got all right? Thank you, Junji. Okay, so we're good. Now we have our way of converting numbers into floats. And yes, this is most definitely examinable, so I would practice a couple of these examples. But as you can see, it's not that hard once you get the gist of it. They're just have to follow the steps. Which takes us to our last operators. We've used the plus, minus, size of, divided by, times operators. We've used the and or operators. But now that we're playing around with bits, it's time to introduce a few more of these. These are operators that work specifically on the binary representations of numbers. So we'll come back to that first point, but our operators are shift left, shift right, bitwise or, bitwise and, bitwise XOR, and bitwise complement. So let's go through what each of these operators do one by one. And this will be a fairly quick thing. I would really recommend looking at the book or a reference just to remember what they are while you're still getting used to them. Okay, so let's take a sample number. Let's do this number. Okay, the first operator we're going to look at is the shift left operator. So the shift left operator says take all the bits and move them one place left. And let's imagine we are working with a 6-bit with a 6-bit number. So these are all the bits we have. There's not room in the computer for any more bits. Those are all the bits we have. So shift left is going to take all our bits and move them one position in the integer to the left. But Junji, do you want to pass the microphone back to, I don't know, Ashwin? What is the problem if I shift my bits to the left? What's going to happen? Turn on the thing. Will the number decrease or the number increase? Number will increase. That doesn't sound like a problem. That sounds like a good thing. What happens if I put a number 1 here and I do a shift to the left? So if I'm using a signed integer, but we can also represent things as unsigned integers. So we can reclaim that first bit and say, just treat this whole thing as one big number. And that's what we're going to do right now. So this is our number. It is going to be, this number is 44. Now what we're going to do is we're going to try a different number. We're going to change that to a 0. What number do we have now? Oh, Max, what's my new number, given that I made a mistake the first time? So my new number is 12. Okay, now I do a left shift, and I've moved all the bits up one place. So I have 0 contribution from there, 0 in the 2's place, 0 in the 4's place. I have 8 from the 8's place, and 16 from the 16th place, and 0 from the 32's place? 24. So what is the relationship between 12 and 24? I've doubled it. So every time I do a left shift, that's going to be equivalent to a multiplication by 2. Now, we also have another operator, and unsurprisingly, this one is called the right shift operator. And so what does my right shift operator do? It halves it. So it moves all the bits over by one place to the right, dropping off whatever the rightmost bit was, and is going to end up halving our numbers. So there are 2 of our operations.
Sorry, just what if the last one was a 1? Are you saying
It just falls off the edge and you get a 0 on the other side.
it doesn't actually double it?
Not quite.
Okay.
But you have to be careful about the doubling in particular. You'll still get a halving, but it'll be truncated. For the doubling, you have to watch to make sure that you're not overflowing your integer. But that's no different to normal integers. When you do operations, you can overflow them. Afan?
Oh.
You really want more questions?
No. Wait, yeah.
You're going to hand it back to Max after. No, ask your question.
Where would this be used then?
So if you want to do really efficient things, you want to do very efficient multiplications by 2, this can be great. Or if you're trying to actually manipulate the bits themselves, this can be a powerful operation. So for example, when you see a lot of numerical computing or things that are very high performance, they'll sometimes take advantage of these operators. Okay, so now we have a couple more operators to get through. We have our AND operator, our OR operator, our XOR, and our complement. And let's start with the complement operator because it's pretty straightforward. Our complement operator switches everything that's a 0 to a 1 and everything that's a 1 to a 0. So the complement would be 1, 0, 1, 0, 0, 1. Why do we call that the complement? Because if you were to add these 2 together, you'd get a full set of 1s. Did I have this one right? Okay, our next operation is the AND operation. So our AND operation is, these operations turn out to be super, super important in microcontroller logic and in actually building computers from the ground up. This is how circuits are going to work. So our AND operation is going to look at 2 numbers at once. So we do number A AND with number B. So let's say that this is A and that's B. And now I ask for A and B. So let's replace that plus sign with the AND operator. And now what we're going to do is we're going to look at both the top and the bottom. And if they're both 1, then we write 1. And if they're not both 1, then we write 0. So in this case, we'll get 0, 0, 0, 0, 0, 0. Why is this? How did I make B? It was the complement. So if I do A and complement B, I'm always going to get all 0s. So that was a bad choice for an example. Let's try a different number.
Does the AND operator, if they're both 0s, does that give you a 1? Or
No, it's only if they're both 1s.
Yeah.
So let's try. Not today. Well, okay, we can do a baby truth table. Yeah, I'm doing that. Okay. 1, 0, 1. And this is what we call a truth table, and you'll probably see these in real analysis if you haven't already. And this is the truth table for the AND operation. So when both elements are 0, you get a 0. When one of the elements is a 1, you get a 0. When one of the elements is just a 1, you get a 0. And when both of them are a 1, you get a 1. Okay, we can also then actually do it out over here. Both of them were a 1, both of them were a 0, both of them were a 0. One of them was a 1, one of them was a 1, one of them was a 1. And in the dying moments of today, let's do this for our other operations. Let's make the truth table. We'll do our OR. And the difference between our AND and our OR in the truth table representation is that now we set it to be a 1 whenever either of them is 1. So this is the difference between AND and OR. Put a 1 there and a 1 there. And now our final number has a lot more 1s in it. because we get a 1 whenever either the top number or the bottom was a 1. And then our last operation, and this is a fun one, this is the XOR operation. This is exclusive OR. This is true when one of the numbers has a 1, but not the other. So it's kind of like a funny version of the AND, or a funny version of the OR. You can think about it like as a mix between them. And we often draw it using this mathematical symbol. I'll draw another one of them, like that, is often used to represent exclusive OR. But in C, because we don't have access to that funny symbol, we are going to use the caret symbol. That's like the, above the number 6 on a standard keyboard is the caret symbol. So let's fix up our truth table for it. It is going to be, XOR will give us 0 when both of them are 0. It will give us 0 when both of them are 1. And it will give us a 1 as long as only one of them is, as long as only one of them is 1. So let's figure out this with our sample number. We get a 1 here. Max, what do I get in the next? 1, 0, 0, 0. And even though there were 2 1s in that column, because the XOR rule is that only one of them can be 1, we still get a 0 in that position. So there are all our fancy new number operations. But before I let you go, I still want to answer this original question that we had of how to represent and how to deal with the Taylor Swift numbers. So we'll do the code demos later. But hopefully now we can identify what notes Taylor Swift was playing. So this is a simple sine wave. Taylor Swift would neither be singing this nor playing this unless she was playing a signal generator. But this is in fact a musical note, and it is the note A. However, the actual frequency, the graph of the frequencies is going to look really different if you play this on a real instrument, because a real instrument is actually going to mix together a bunch of frequencies. You're not going to get a pure sine wave being generated by your instrument. So that was playing an A. What about this one? This one's a little more exciting. It's actually a mixture of 3 sine waves. The sine wave for C, the sine wave for E, and the sine wave for G. And Perrin, what's that? Which triad? That is a C major triad, so just a single strum on the guitar or 3 fingers down on the keyboard. And what we want to do is we want to figure out how we get from this frequency diagram to our note of pianos. We're going to need a very special algorithm for that, and this is one of the crowning jewels of algorithmics, and it's called the fast Fourier transform. And it's a fairly complicated algorithm, but it relies on the sophistication of the floating point representations that we've built up. Or you can do it with fixed point arithmetic, but one way or another, the skills you learned today are the things that allow you to figure out what Taylor Swift was playing. I will see you all tomorrow.